of this code. Now we will learn about semaphore. So semaphore is, what is a semaphore? Semaphore is an integer variable. So we will denote semaphore as s. Uh, so in semaphore you are given two standard atomic operation, wait and signal. So this is the wait code, this is the signal code. Okay. Uh, so this is also a atomic function. You cannot interrupt them in between. So what does the semaphore do? So many times whenever we are accessing some shared variable or common variable, we want to execute them in a certain order. We want to execute them in certain order. Using semaphore, you can achieve this certain order. Okay, you can synchronize multiple processes or multiple threads so that they can execute in a certain order. So here we will see a basic version of semaphore where we will only use the semaphore so that multiple processes cannot run or cannot modify shared variable simultaneously. Okay, so if you need to maintain some order or maintain synchronization, you can use semaphore variable. So you are given two port, wait and signal. Wait and signal. So what is the wait function? Basically, wait function is while s is less than equal 0, it will do nothing. If the value of semaphore is less than equal 0, it will do nothing. Otherwise, it will decrement the value of semaphore. And in signal function, it increments the value of semaphore. It increments the value of semaphore. Okay. So okay. So we will try to achieve mutual exclusion using semaphore. Let's see how we can do that. So there are two types of semaphore. One is binary semaphore, one is counting semaphore. So semaphore s is a integer variable. So in counting semaphore, the value of this variable can range over an unrestricted domain. So you can put any integer value. So the value of semaphore can range over an unrestricted domain. Let's say 0 to 100 or 0 to 50, your choice. So any unrestricted domain, you can put value here. What is the use case of this counting semaphore? So the use of counting semaphore is, one of the use case can be, you can manage the number of, let's say you have 5 resources. Okay, you have 5 trial rooms. So there are multiple instances of a single trial room. So there are 5 trial rooms. They are look-alike. Now you want to give access of these 5 trial rooms to the customers. So you can manage this using counting semaphore. Okay, so we will have some example. So counting semaphore can be used to control access to a given resources consisting of finite number of instances. At first we have only one trial room and everyone is using this single trial room. So you can use test and set or try um, compare and swap, or we saw a software based solution mutex log. So if you have multiple trial rooms, you can manage them or you can give access to them using counting semaphore. And counting semaphore can be used to solve various synchronization problems. We will have some example. Then binary semaphore. So binary semaphore is the value of the semaphore variable can be in between 0 or 1. It will be either 0 or it will be either 1. Binary semaphore behaves similar to mutex log. So the behavior of binary semaphore is same as mutex log. Okay. Now we will have an example of counting semaphore. Let's say you have 3 trial rooms. Okay. So the customer will come and can acquire any of the trial room. The customer can come and acquire any of the trial room. So every time you need to one customer comes, you need to check any of the trial rooms are is free or not. Okay. So we can easily simulate this behavior using counting semaphore. Initially, the value of the semaphore will be the number of available resources here. So initially the value is 3. Initially the value is 3. Okay. So that means 3 trial rooms are available. 3 trial room. So initially 3 trial rooms are available. Whenever a customer comes, he need to check any of the trial rooms is available or not. So it will check the semaphore variable using the wait function. So what the wait function do? While s less than equals 0, do nothing, s minus minus. So initially the value of s is equal to 3. So 3 will be passed here. While s less than 3, 3 is less than equal 0. That means the condition is true. That means at least one of the trial rooms is available, s minus minus. So the value of s will be decremented. Is equal to. That means it acquires a trial room. Now the available trial rooms is 2. So customer 1 is using the trial room. Let's say another customer comes. It will also call the wait function. So now the value of s, which is true, will be passed. 2 is less than equal 0. That means at least one of the trial rooms is available. Then we will s minus minus s equal to 1. Let's say customer 2 is using another trial room. Let's say another customer comes. It will call the wait function. So the value of s is equal to 1. 1 less than equal 0. That means at least one of the trial rooms is available. It will decrement the value 0. So customer 3 is using the trial room. Now another customer comes. Customer 4, it will call the wait function. So here the value will be 0. 0 is less than equal 0. So the condition is true. That means it will stuck in this while loop. It will do nothing. There are no available trial room. So it will stuck in the while loop or it will do nothing and waiting. Okay. So that's how if there are multiple instances of same resources, you can manage them or give access to them using semaphore. Now let's say one of the customers C1 uh, want to leave the trial room, so it will call the release function. So what does the release function do? S plus plus. So customer 1 wants to leave, so now the value of S will be passed. Value of S, current value of S is equal to 0. S plus plus means S will be 1. That means if customer 1 leaves, 1 trial room will be available. Now customer 4 can access it. So in this way you can manage the resources. So initially you will initialize the value of semaphore as the number of resources available. Then whenever a process wants to access any resources, it will call the wait function to check any of the resources is available or not. If any of the resources is available, it will acquire it and the available resource count will be decremented. Whenever a process releases a resource, it will call the signal function or release function. Signal function and release function is same. So we'll call this signal function. Signal function. So it will call the signal function. So that means available resource count will be incremented. If S becomes 0, that means all resources are used. So until S becomes greater than 0, all other resources wish to access the trial room or the resources will be blocked. They cannot access the resources if S is less than or equal to 0. If no other resources available, no process can access the resource. So until S greater than equal 0, that means at least one of the processes, sorry, one of the resources is not available, all other processes will be blocked. So in this way you can use semaphore, counting semaphore. Now binary semaphore. So we will see an example how to synchronize using binary semaphore. Let's say there is a process P1. It prints the value CSC, and there is a process P2 which prints the value 321. There is a process P1 which prints CSC, and there is a process P2 which prints 321. So in the output, let's say P1 and P2 are executed simultaneously. P1 and P2 are executed simultaneously. So the output can be CSC 321 or the output can be 321 CSC. If P1 is executed first, then P2, the output will be CSC 321. If the P2 process is executed first and P1 is executed later, then the output will be 321 CSC. So these are the possible output. Now we want to print. We want to print CSC 321. We want to print CSC 321. That means we want to force to process P1 to be executed first. After that, P2 will be executed. So how to do this? P1 and P2 are running or executing concurrently, but we want to execute P1 first and then P2. How to do that? So we will use a semaphore S. Okay, so semaphore, binary semaphore S. Let's say S is equal to 0. So P1 and P2, it will print CSC, it will print 321. So we want to get the CSC first and then we want 321. So as there is only one way or one condition. Let's say at first P1 and then P2, only one condition. So we can use a binary semaphore. So how can we do that? We need to block the execution of P2. So we will call a wait function. What the wait function do? While s less than equals 0, we will do nothing. S minus minus. So using the wait function, as s is initialized to 0, using the wait function, we blocked the execution of P2, because if s is less than equals 0, it will stuck in this while loop. So we blocked the execution of P2. If P2 is scheduled fast, it can't progress from wait. That means printing 321 is blocked. So after some time P1 will be scheduled. So it will print CSE. It will print CSE. Then we want to let P2 know that I am done executing. So it will signal. So in the signal function, we use s plus plus. So the value of s will be 1. If the value of s will be 1, then P2 can come out from this while loop. Then it will use s minus minus, and then it can print CS321. So in this way, you can achieve synchronization. So whenever there is a execution order, so we want P1 at first, then P2, there is an execution order. For every execution order, you need to use a semaphore variable. For every execution order, you need to use semaphore variable. Let's say here are another example. So let's say P1 prints C, P2 prints S, P3 print E. Okay. So in the out P1, P2 and P3 are three processes. They are running concurrently. So any of the process can be scheduled and any of the process can print its corresponding output. But in the output we want CSE. In the output we want CSE. That means the order is P1 will be executed first, then P2, then P3. So there are two different execution order. So for this execution order P1 to P2 we will use a semaphore S1. From P2 to P3 we will use a semaphore S2. Initially S1 is equal to 0, S2 is equal to 0. So P1 prints C, P2 prints S, P3 prints E. Okay, so we want to block the execution of P2 so that it can be executed before P1. So we will wait until P1 is finished. Whenever P1 is finished, it will signal P2 using the semaphore variable as 1. Again, for P3, we want to block the execution of P3 until P2 is finished. So it will wait for P2 to be finished using the semaphore S2, and it will, after the execution of P2, it will signal P3. So P1, P2, P3, they can execute it in any order. Let's say P2 is scheduled first, but it will be stuck in this wait S1 as S1 is equal to 0. If P3 is scheduled first, it will stuck in this wait loop because S2 is equal to 0. After some time P1 will be scheduled, then it will print C. then it will signal S1. That means S1 will be 1. When S1 is equal to 1, this wait function can progress forward. So then it will print S. Then it will signal S2. Whenever S2 is equal to 1, this wait loop can progress forward and it will print T. In this way, you can achieve the synchronization. So whenever there are some synchronization order or the execution order, you can use semaphore, binary semaphore to achieve it. You don't need to use binary semaphore. You can also use counting semaphore. You can play around with this semaphore value. So that's how whenever you are given a synchronization problem, you can take help from the semaphores. You can achieve mutual exclusion using semaphore. The binary semaphore exactly works as mutex. So let's say in mutex there are two functions, acquire and release. In acquire function, you check availability. You check availability. And in the release function, you release the resources. So if the binary semaphore value, so in the mutex there is a value called available. Initially the value is available is equal to 1. There is a acquire function. While it's not available, do nothing. Avail sorry. Uh, Available minus minus or available is equal to 0. In the release function, available is equal to 1. So in the binary semaphore, so initially the value of the semaphore is equal to 1. Here as represents the availability. So there is a wait function while as less than equal 0, do nothing. Do nothing. As equal 0, and in the signal function s equal 1. So you can see both are the codes looks similar. So basically here in the binary semaphore, the semaphore value s represents the availability. So you can achieve the behavior of mutex using binary semaphore. So okay, this is it. Now we will implement semaphore. Here the wait and signal are dynamic functions, and you must guarantee no two processes can execute the wait and signal function on the same semaphore at the same time. So this implementation is quite critical. So okay, in the wait code, while s less than equal 0, it do nothing. Then s minus minus. So you can see whenever a process is calling the wait function, it checks the while condition. If s is less than equals 0, then it is stuck in this while loop. So every time it calls the wait function, every time it checks the while loop condition, and if the condition is true, that means s equal less than equals 0, it got stuck in this while loop. That means it is only looping through this while loop. So this is known as busy waiting. It is also called spinning. So it is known as busy waiting. So the problem is that the busy waiting implementation is easy, but sometimes if it is too big, if the waiting is too big or too large, it wastes a lot of CPU cycle. So we will see a better version of this later. So if if the applications spend a lot of time in critical sections, that means all other processes uh, will be spinning in this while loop. That means we'll be busy waiting and will waste the CPU cycle. So you need to remember it. The implementation is easy, but the problem is it will waste a lot of CPU cycle. If the critical section is little or it is rarely occupied, then you can use this implementation because it is simple to implement, but there are some problems if the critical section is too large. Okay. So how to mitigate this issue? So if any process is executing its critical section, all other processes are busy waiting. That means they are looping through the while loop and wasting the CPU cycles. How to mitigate this issue? So basically, one of the solutions can be whenever a process sees that it can't access the critical section. Whenever a process understands that it can't access the critical section now. So the best way is the process can block itself. So it will not occupy the CPU again to checking the resources again and again. So rather it will place itself in the waiting queue of a semaphore. It will place itself in the waiting queue associated with the semaphore. So in the semaphore value as, so in the wait function for the semaphore value as, we are checking the while loop again and again and again and wasting the CPU cycle. Rather it will not check again and again and place it in the waiting queue associated with the semaphore. So the process scheduler will know, the CPU scheduler will know that this process is blocked and we do not need to schedule it again and again. It can schedule another process. So whenever the signal function will be called, then we will restart the blocked process. We'll wake up the blocked process. So let's say an example. So in the semaphore value, we'll store an integer value. The semaphore value is an integer value, and with this, it will maintain a process list. Whenever our process called wait function, if the semaphore value less than 0, that means no other resources are available, it will place itself in the waiting list. This is the waiting list associated with the semaphore. it will block itself and place itself in the waiting list. It will block itself and place it in the waiting list. Whenever there is a signal value, whenever there is a big signal value, we will remove a process from the waiting list and restart it again. That means wake up. We will wake it up. So rather than busy waiting, we will block the process and keep it in the waiting list or waiting queue of associated with the semaphore. Whenever there is a signal call, we will wake it up again. We will remove it from the waiting list and wake it up again. So in this way, you can mitigate the busy waiting issue. So in this list, you actually store the PCB, actually the pointer to the PCB of this process. So here is the another code. Here we used semaphore to recreate the value of mutex. It is the same code we saw in the mutex example. This is the similar code. Before accessing the sum value, we need to call the wait to check we can access the sum value or not. And after using the critical section, we will signal the value. So I hope I do not need to teach it again. So this is the so how can you initialize the semaphore value? This is the initialization value. This one is the initialization value. That means semaphore s is equal to 1. Okay. 0 means this is the value called p shared. You will learn more about this in your lab session. But to initialize value, you need to pass the semaphore variable. Then this is the value for p shared. And if it is 0, that means the semaphore is not shared. Then it is the initial value of the semaphore. That means s is equal to 1. So if you understand the mutex example, this is also same. We also saw how using binary semaphore you can replicate the mutex behavior. Now we will learn about application of semaphore